A gravitational wave is passing through your body right now. Your head and feet just moved a tiny bit farther apart, then a tiny bit closer together, then farther again, oscillating at roughly 100 times per second. The stretch was incomprehensibly small, something like 1/10,000th the diameter of a proton. You felt nothing. But here's what's unsettling. The wave that just ghosted through you was generated by two black holes, each about 30 times the mass of the Sun, that spiraled into each other and merged roughly 1 billion years ago in a galaxy so far away you'll never see it. The energy released in the final fraction of a second was greater than all the light from all the stars in the observable universe combined. And yet, by the time that energy reached you, all it could manage was to stretch you by less than the width of an atom. Get closer, though, much closer, and the same physics becomes lethal in a way no science fiction has captured. Near the merging black holes, space-time itself oscillates so violently that no object could hold together. Not because of gravity's pull, not because of temperature or radiation, because the distances between your atoms would stretch and compress at different rates, ripping you apart without any force ever touching you. How can nothing, literally just empty space, tear you apart? The answer lies in what gravity actually is, and it's not what most people think. Einstein discovered that gravity isn't a force pulling you down, it's the shape of space-time telling matter where to go. The Earth doesn't tug on you, it bends the space-time around it, and your straight-line motion through that curved geometry looks like falling. But here's the insight that changes everything. When mass accelerates, when it spirals, merges, collapses, or explodes, it doesn't just curve space-time, it creates ripples in that curvature, ripples that propagate outward at exactly the speed of light. These ripples are gravitational waves, and when a gravitational wave passes through you, it doesn't push or pull, it stretches and squeezes space itself. You stretch and squeeze with it because you exist within space. The wave doesn't exert a force on you, it changes the geometry you're embedded in. This single principle, accelerating mass creates ripples in space-time, will explain every phenomenon in this video, from the most precise measurement humans have ever made to the origin of the gold in your jewelry, to faint signals that may tarry whispers of the universe's first moments. For nearly a century after Einstein predicted gravitational waves in 1916, many physicists weren't sure they were real. Einstein himself flip-flopped. In 1936, he submitted a paper arguing gravitational waves couldn't exist, that they were a mathematical artifact with no physical reality. A referee rejected the paper and pointed out his error. Einstein eventually changed his conclusion. The problem was that space-time is stiff, absurdly stiff. To produce a gravitational wave strong enough to notice, you need masses moving at significant fractions of the speed of light. And even then, by the time the wave travels astronomical distances, the stretching it produces is unthinkably tiny. How tiny? LIGO, the Laser Interferometer Gravitational Wave Observatory, measures changes in length of about 1/10,000th the diameter of a proton. To put this in perspective, if you scaled LIGO's 4-kilometer arms to the distance between Earth and the nearest star, the change they're detecting would be less than the width of a human hair. Building a machine this sensitive took 40 years. The story begins in the 1960s with Rainer Weiss, a physicist at MIT, teaching a course on general relativity. He realized he couldn't actually explain how gravitational waves might be detected. So he worked it out. His solution: 2 perpendicular laser beams bouncing between mirrors. A gravitational wave stretches space in one direction while squeezing it in the perpendicular direction. If you shoot identical laser beams down two perpendicular paths and recombine them, they should arrive perfectly in sync. But if a gravitational wave passes through, one path gets longer while the other gets shorter. The light beams arrive slightly out of phase. The mismatch reveals the wave. Simple in principle, nightmarishly difficult in practice. The instrument has to filter out every other vibration on Earth. Trucks driving on highways miles away, waves crashing on coastlines, seismic tremors from human footsteps. The team suspended mirrors from 4 stages of pendulums, isolated lasers in vacuum chambers, and built 2 identical detectors, one in Louisiana, one in Washington State, so they could confirm any signal appeared at both locations. On September 14, 2015, at 5:51 a.m. Eastern Time, both detectors registered an identical signal. The pattern was unmistakable, a chirp. The frequency started low, rose rapidly, then cut off. This was exactly what Einstein's equations predicted for 2 massive objects spiraling closer, orbiting faster and faster, then merging. The analysis revealed 2 black holes, one 36 times the Sun's mass, the other 29. They had spiraled together, moving at roughly 60% the speed of light in their final orbits, then merged into a single black hole of 62 solar masses. 3 solar masses, the mass of 3 suns, converted entirely into gravitational energy in under a second. For the first time, humans heard spacetime ripple. That detection confirmed the spine. Accelerating mass creates spacetime ripples. But binary black holes are invisible except for their gravity. What happens when the same physics, the same spiral, the same merger, involves objects that can produce light? On August 17, 2017, LIGO detected another signal, but this one lasted nearly 2 minutes. The chirp rose more slowly. And analysis showed the merging objects were much lighter, roughly 1.5 solar masses each, not black holes, neutron stars. Neutron stars are what remains when a star between 8 and 25 times the Sun's mass dies. The core collapses until protons and electrons crush together into neutrons. The result is a ball of matter about 12 miles across with the mass of the Sun, where a teaspoon weighs 1 billion tons. And unlike black holes, neutron stars are made of matter. When they merge, they don't just ripple spacetime, they explode. Exactly 1.7 seconds after the gravitational wave reached LIGO, NASA's Fermi satellite detected a gamma-ray burst from the same region of sky. Telescopes worldwide swung toward the source. In NGC 4993, 93 million light-years away, they found a new point of light. This was the kilonova, the afterglow of 2 neutron stars colliding. As they merged, material flung outward at 30% the speed of light. In this debris, freed neutrons slammed into atomic nuclei so fast that the nuclei couldn't decay before absorbing more. This rapid neutron capture built the heaviest elements, gold, platinum, uranium, in seconds. The kilonova glowed because newly formed heavy elements heated the debris. Spectroscopy confirmed strontium and likely other heavy elements. This single event answered a decades-old question: where do the heaviest elements come from? Supernovae don't produce enough. The answer was here. Neutron star mergers are cosmic forges, and gravitational waves led us to watch one happen. Remember the spine. Accelerating mass creates spacetime ripples. LIGO hears waves from stellar mass objects, black holes and neutron stars, up to roughly 100 solar masses. But the same principle operates at every scale. Supermassive black holes, millions to billions of solar masses, merge when galaxies collide. Their orbits take millions of years, producing waves with periods far too long for LIGO. But pulsars, rapidly spinning neutron stars emitting precise radio beams, act as natural clocks scattered across the galaxy. A passing gravitational wave stretches space between Earth and distant pulsars, changing how long their pulses take to arrive. By monitoring dozens of pulsars for decades, astronomers can detect this collective wobble. In 2023, pulsar timing arrays worldwide announced evidence for exactly this, a background hum of gravitational waves, likely from countless supermassive black hole pairs spiraling across the cosmos. The universe is full of deep rumbles we're only now learning to hear. Future space-based detectors like LISA, 3 spacecraft millions of kilometers apart connected by lasers, will hear frequencies between LIGO and pulsar arrays. This band includes white dwarf binaries in our own galaxy, providing a constant gravitational hum against which mergers will appear. And then the ultimate target, primordial gravitational waves from the universe's first fraction of a second, potentially generated by inflation, the explosive expansion that seeded all cosmic structure. Detecting these would mean seeing farther back than any telescope can look, to an epoch when space-time itself rang from its violent birth. So, a wave is stretching you right now, but not enough to feel. The same physics that produces that ghostly oscillation also forged the gold in your jewelry, generates the background hum of merging monster black holes, and may carry imprints from before atoms existed. Can gravitational waves from cosmic events harm you? No. Space-time is too stiff, and the sources are too far. But the point was never survival. The point was understanding. For 3 centuries after Newton, we thought gravity was a force acting instantly across space. Einstein revealed it was the shape of space-time. But for another century, we could only observe gravity's static effects, curved paths, bent light, orbital precession. Gravitational waves opened a new sense entirely. We now hear the universe, not just see it. And in that sound, we found black holes we couldn't see, watched neutron stars we couldn't otherwise observe, and discovered where the heaviest elements originate. There's something strangely intimate in this. The wave stretching you right now has traveled for 1 billion years to deliver a message. Somewhere in the cosmos, mass accelerated violently enough to make space-time vibrate. That vibration crossed incomprehensible distances, passed through galaxies and stars and planets, and arrived at you. It changed the distance between your atoms by an amount too small to feel, but not too small to measure now that we've built ears for the universe. The cosmos was never silent, we just couldn't hear. And now that we can, the question isn't what we'll find. It's what we'll finally understand. Like if this was interesting, hit the subscribe for more and turn that notification bell on.